planets. That was the original. Glad he's going to tell us about CoRoT 7 as well. Great topic.
Okay, good afternoon. Well, I will talk about the two new planets that have been discovered by the Space Telescope CoRoT. The name of the star now is CoRoT 7 because it's the seventh star showing a planet discovered by CoRoT. And here is a little bit of imagination of what may be one of them, the inner one. Well, first, quickly, the first result. The first result was a dim in the light of the star, okay, every 20 hours more or less. So what you have here is many intervals that were put together, all of them with the exact period to show the dim. And here is the average of that mass, and what you see is that this is very small dim. You see is 3 in 10,000. So this is the kind of precision that is possible to make measurements in space. One of the difficulties, in fact, that we had with CoRoT, not only in the study of exoplanets, because CoRoT is half a study of exoplanets, half a study of seismology of stars, is that there is a zoo of different light curves that we don't know how to interpret, because we never had before, for so many stars, for so long time. It's 150 days each run, so the star is observed 150 days continuously with this precision. So there is a lot of new phenomena that are being discovered thanks to this precision. Well, the problem when we get a dim in the light like that one, we would like that in every case we get a planet, but this is not true in most of situations like that one reveal itself as being a false alarm. It's not a planet around the star, but it is it's a binary, and which is passing very tangentially, so it makes just a small dim in the light. Or then you have a giant star, and this is a dwarf that is passing in front, and also mimics the same case that for a planet. Or this is more tricky. You have an eclipse binary in a tripole star. So when we add everything, the dim is very small, but because the variations here comes from are added to the light of a strong star that is there. So the first thing to do is to look if this is not the case. So once the planet was suspected, lots of astronomical observations were done to see if you don't have just behind one system like this one, that whose light is being added to the light of the star, and whose variation would mimic the existence of a planet around the stars. But you see, the only ones that are inside the field are very small, and we don't need to take care of them. But the real test to believe that a dim in the light corresponds to a planet is that we must see a variation, a periodic variation in the velocity of the star. So, and this is the second critical point in CoRoT, is that we are making, for instance, in this first case, we have a planet whose mass is about 5 Earth masses. the variation of the speed of the star around the gravity, the center of gravity of this system because of this planet is only 4 meters per second. So you need to have a spectrograph able to make measurements with the precision of 1 meter per second. 1 meter per second, remember, make a quick calculation. 1 meter per second is 3.5 kilometers per hour. So it's the speed that we have when we go walking on the street. So we need to have measurements of the velocity of the star with this precision if you want to confirm that the variation of the light that has been observed, that it was indeed a transit by a planet. So some measurements were done with HARPS. HARPS is the most precise spectrograph working nowadays. He is in ISO in Chile. Okay, and we have seen the variation of the radial velocity. So several measurements of radial velocity, and they were folded with the period of the transit, and we can see that indeed there is a variation of the radial velocity that whose period corresponds exactly to the period of the transit. So this confirms that the first observation is a planet. Well, so one first determination was done, and this first determination, okay, pointed to a planet with 6 Earth masses, and you see the speed, the variation of the velocity of the star around the barycenter of the system is only 4 meters per second. Well, this was enough to say that this is a very interesting object, and it must be more carefully observed. So, people having time on the spectrograph have given part of their time so that this object could be studied, and 109 observations were done with this precision of about 1 meter per second. Okay, when you look here, it's very beautiful, but you know the red line, the red line is a trick. If you take it, you just have a mess. When you have the red line, you see, oh, it's very well, it's very regular variation, but this is just to trompe l'œil, like say the French, it's just to make your eye foolish. But in fact, if you take it out the red line, you don't see any regularity in this variation. So the analysis is very difficult. And the analysis is very difficult because one of the things that has been revealed by the photometric observations is that this star is a very active star. Presumably, it's full of spots, like the sun. These spots, okay, they are rotating with the star. They are not permanent features. If they were permanent features, no problem. But like in the sun, you have spots that come and go. Okay, so we don't know. We have a variation in the star, which is due to these spots. And this variation also affects the radial velocity, the measure of the radial velocity, because one of the when you measure the radial velocity of the star, every part of the star is contributing to the velocity, to the measurement done. If one part has a big spot, the velocities of that part don't enter in the average. They are because it is occulted by the spot. Okay, so you have the star is turning like that. Okay, if there is an obstruction of part of the light coming from here, this part will predominate, and I will have a velocity larger in that direction. When the spot is that light, I will have another in this direction. So there is a variation of the radial velocity, whose period corresponds to the period of the star. And here are then the observations, these dots. And here is a model of the variation which is associated with the spots on the star. Let me say that the observations does not measure only the radial velocity. The width of the spectral line is measured because there are variations of the width when one part of the star contributes less than the other part. The profile, the center at several eighths of intensity, okay, it should be a straight line, okay, it's this bisector, some fluctuation. This is also measured, and there is also measured some parameters related to the calcium lines of the star, which becomes in this case more strong. So there are other parameters that we can measure to check the variation of the activity of the star, and they follow more or less a pattern like this one. And also, at the same time as the spectra, the photometry was being done. So we have also the photometric record showing this kind of variation. However, I should say that there is in the CoRoT team a discussion about this, because it's obvious that okay, some methods were used to obtain this estimation of the activity of the star, but some people claim that small variations doesn't appear here, okay, and some of these variations that we see here are not exactly coming from a variation due to planets, but are also due to the variation of the star, are also due, to the activity of the star. And there are others in the other side that claim that they have been cleaned too much, and part of the signal of the planets can have disappeared with the cleaning. Okay, there is some kind of arbitrarity in the way in which this is done. Okay, in this case, this has been done using a statistical method, using a window, and making smoothing, running averages inside the window to take out the small variations in small intervals, and the method that has been used is very good. But anyway, this is the weak point in this determination. And okay, sorry. Once the activity was estimated, it's possible to know which part of the signal corresponds, is not due to the activity of the star, is due to another reason, due to the planet, for instance. And then we have these oscillations here. This is the residual of this cleaning of the signal. So is the signal, this is the velocities as they are measured, and these are the residuals after subtracting what is supposed to be the activity of the star. Okay, so we remain with this, and we make a first periodogram of the results of the residuals, and surprise, the most important peak we find is not the planet that has been discovered. It has a different it has a different period, 3.7 days. Okay. Okay, this is there is one problem. The fate of the astronomers is to observe at night. So in this case, all observations are done at the same place. So all observations are done when the star is close to the meridian. So all observations are separated one from the other for multiples of 1 sidereal day. So this creates reflection. This creates foldings of the time. You cannot make nothing correctly. 4 frequencies is larger than this one. 4 periods is smaller than 2 days. So usually when you do this with other kind of signals that you can, we work with larger periods. So we start the work more or less from here, okay? From here to here. We forget that part. That part has high frequencies, very small periods. But in this case, we do not have the choice. The Nyquist period is 2 days. And we are working with a star that has 0.85 days of period. So we have to look the spectrum, the Fourier transform, in one region in which theoretically we should not, we should forget about, but we need of it. So we see there are reflections here, there are reflection here, there is a reflection here. So at every 0.5 in frequency, the spectrum is reflected. So this peak is the same as this one, is the same as this one, is the same as this one. Okay, knowing that, being aware of that, my colleagues try to make several observations during the same night. For instance, to make an observation, if possible, at the beginning of night, and another observation at the end of night. So to break this periodicity of the observations. You see, for instance, here 3 observations, one after the other. You see one group of 3 observations, 3 observations. So these are observations done in the same night. So in order to avoid this periodicity of the time series. And so, in fact, if this was not done, probably the 4 peaks would be exactly the same size. Mathematically, you could not say that one is better than the other. But since some observations were done trying to escape of this periodicity, you see the peaks are not exactly at the same height, and we can believe that this one is the right one that corresponds to 3.7 days. The other ones, the frequency is higher, the period is lesser. Okay, once this period is, so this signal, corresponds to a second planet that is beyond CoRoT 7b. So this is CoRoT 7c. So once cleared the signal of the other, then the signal of our planet appears very well. And again, in this case, this peak, okay, there is a reflection here, more or less about here, okay, but this peak is very well dominant over the others. And on the other hand, for this planet, we have transits that have been observed. So we know that this is the period. So here are the results. CoRoT 7b, period about 20 hours. Mass 4.8 solar Earth masses, and the radius 0.017, 4.2 R star. Well, this is important because this is the smaller planet for which both data are available. So if I have the mass and I have the radius, we can have a good estimate of the density of the planet. In this case, the density is corresponds more or less to the density of the Earth. Not very different. Well, there is a huge error bar here, about 1 Earth mass, because of the difficulties that I have shown you showed to you about the difficulties to separate what is activity of the star and what is planet. And the second planet, CoRoT 7c, with a mass of 8.4 Hertz masses, also with the same uncertainty, at 0.046 AU. Sorry, I made a mistake. Here is the same major axis of the orbit, 0.070 AU, 4.2 star radii. The radii of the star is not yet here. It will appear. So, anyway, from the observations of transits, we can get the radius, and then from the radius and the mass, we can have estimation. We can start making some conjectures about what this planet is. So we see that he is more or less at the boundary of, more or less silicates dominating, but with maybe a bit of iron. Okay, so we expect to have it more or less like the Earth. So here is the Earth. Here is a drawing of what can be CoRoT 7b. What is important in this case is that the rotation is synchronized with the orbit in such a way that one side of the planet is always the same, looking at the sun. So it's much more other than the far side, and the temperatures must reach easily about 2000 degrees centigrade in the illuminated face of the side of the planet. 2000 degrees is enough to melt silicates, so we must have a kind of lava ocean over the planet. Well, let's study a little bit of the dynamics of this system. The first thing we can do is to use the Roche model to study the dimensions of the planet. So here is the radius that comes from the measurement, the mean radius that comes from the measurements of the transit. And if we apply the model of Roche, the Roche ellipsoid, we can estimate that the axis in the direction of the planet, of the star, sorry, compared to the polar axis of rotation, is about 280 kilometers. Or if I compare to the minor axis in the equator, so the ellipticity of the equator, I have here 210 kilometers. This is just with Roche model as if the body was homogeneous. If you take in consideration the distribution of the masses, we know for the Hertz that we have applied a correction, and we apply the same correction for this planet, and anyway, we get that the same major major axis of the same major axis of the ellipsoid is about 200 kilometers larger than the polar semi-axis of the ellipsoid. So this for the static tide. For the dynamic tide, we have to apply a model. The model that has been used is the model due to Mignard. Mignard says that the distance when I compute the potential of the force that are attracting the body, the distance that I have taken is not the distance at that very moment, but the distance corrected of a small factor delta t. This small factor delta t comes from the fact that the body is not perfectly elastic. It takes some time to respond to an external, to relax to the action coming from outside. And in this moment also there is a rotation of the body, and we have to consider also this fact that not only there is a delay in the response, But when I get the response, the body has already rotated a little bit. And this is the result for the force. Just to make a point, this is exactly the same force that is being nowadays used by several authors. It has been deduced also by Eggleton and others, but just the coefficient is different because he considers physics differently of what was considered by Mignard, but obviously both things are equivalent. The important part of the law is this one that says how the force acting on the planets depends on the distance and the velocity and the rotational velocity and the delay of the delay of the tidal. What is interesting also in this case is to say that this force reproduces exactly what we obtain with classical theories like theories of Darwin or more recent the theory of Cauchy. If we take the theories of Darwin or Cauchy and make expansions to the third degree, okay, if I third degree and eccentricity is an inclination, and I do the same with this, we obtain exactly the same thing. So what we are using here is in fact the same thing that the Darwin theory, but assuming that there is a constant time lag and a constant log number k. In the original theory of Darwin, we are free to say that to establish laws relating the time lag and relating the log number k that measures which appears here. We can take it as function of the frequency of the tidal wave, and so it will vary from one frequency to another. A very tricky business indeed. Okay, if I do that and I play with a toy model, in this toy model, okay, first before the toy model, this is the factor that relates that compares. We have two tides. We have the tide of the star on the planet, and we have the tide of the planet on the star. Okay, the planet is attracting the star is attracting the planet. Both are deformed. Obviously, the star is a very thin deformation, and since the star has a very thin deformation because the mass of the planet is small, this quantity is much larger than 1, and so we can say that at least as far as the eccentricity is positive, the tides in the planet are much more important than the tides in the star. The tides in the planet act on a scale of 1 million years. The tide on the star is on a scale at least 10 to 100 times larger. If we consider only the inner planet, the CoRoT 7b, we can use these classical formulas to know the variations of the same major axis and the variation of the eccentricity. What is important here is the following. Both are negative. Both are proportional to powers of the eccentricity. So let's look at this. Okay, what this one says that the planet's falling down on the star. Okay, because of the tides on the planet, the orbit is spiraling inside. This other says that the eccentricity is decreasing. But if the eccentricity is decreasing, at a given moment, the eccentricity will become equal to 0, or very close to 0. And when the eccentricity becomes very equal to 0, the same major axis stops decreasing. So the effect of the planet is very important, but it is short. Because as soon as the orbit is circularized, it stops and only remains the effects of the mechanic, the effects due to the tides that the planet creates in the star. And these are very small, and as I said, acts only in a time scale of the order of hundreds of million years. Well, so a toy model, star, 2 planets, several hypotheses. One of them, no longer the interactions with a disk. We assume that the 2 planets are already formed. Okay, there's no disk to put additional forces. We neglect tides in the outer planet. Tides in the outer planet can be neglected because I don't know if in this equation we can see it. Yeah. You see here, these effects appear the same measure axis in denominator with a power 5. So if you go twice as far, the variations will be 2 power 5 smaller than in the other case. So we can, without any problems,
Can I ask a quick question?
neglect. Yes, please.
Sorry, so in those equations, is the assumption that the spin of the planet synchronizes very quickly,
Yeah.
and all the angular momentum exchanges between the spin of the star and the orbit of the planet, or the orbit of the system? Is that the rough idea then? So you take orbital angular momentum and put it into the star's spin, but you're not.
Yeah,
modeling
the angular momentum, the angular moment of the okay, it will synchronize. I will talk about it.
Yeah.
Okay, and but the synchronization will only be completed when the eccentricity is equal to 0.
Of the planet.
Okay, yeah.
Okay.
So the 2 things goes together, and in general, the bigger chance of an angular moment will be concerning the angular moment of the orbits. The angular moment of the planets very small.
But I'm assuming that the assumption, because you're not modeling the spin of the star in those equations, right? You're ignoring the star.
Yeah.
And so presumably the assumption is that the angular momentum exchanges between the orbit and the star's spin, is that right? Which you're not including, but that must be...
Well, it's not including in the example.
Ah, okay, okay.
It's not including in
So
this
the
example.
exchange between the spin of the planet and the orbit of the planet.
But the spin of as I said before,
Okay.
the variations because of the tides on the star are
Okay.
10 to more than 100 times is lower than this one. So
see.
in this,
Okay.
for these calculations, I can neglect. Otherwise, no.
Okay.
Otherwise, I have
No,
to
no,
take
I see.
them into
Okay.
consideration.
Well, perhaps I could just comment on that. It is an exchange between the orbit and the stellar spin,
Okay.
but in this constant Q, well, no, it depends on the tidal model, but it may not matter how slowly the star is spinning, as long as it's slower than the orbit,
Yes, sure, that's right.
then that formula
Okay, isn't valid.
doesn't depend on the spin rate of the star.
And so, okay, I'm with you. So all the math, yeah.
Yeah. Okay. So the tides of the star are neglected. They are important, but in a giga-years time scale only. Initial conditions are chosen such that the system angular momentum is the same of the first orbit as determined by CoRoT plus radial velocities. And the initial conditions are chosen such that the initial system is gravitationally stationary, is to a constant eccentricity and delta pi. This means the following. I have the 2 orbits aligned. This is the shortest way to say it. In the example, this will be more clear. So, variation of the eccentricities first. So, initial conditions, to have initial conditions given the same angular momentum as we have now, orbital angular momentum, I have to put the 2 eccentricities very high. okay? And the two eccentricities are damped, not only the eccentricity of the inner planet, and this I will explain later. Both eccentricities are damped, even if only tides on the inner planet are considered. The damping of E2 is a consequence of the conservation of total angular momentum. There is a transparency showing this later on. And the second eccentricity also is damped to very small values. Same major axis. Okay, the same major axis of the same major axis of the outer planet is almost constant. In general, at least far off the resonances, there is no transfer of energy between the orbits. Okay, this is well known that in circular motion, same major axes of the orbits are not affected. While the same major axis of the inner planet decreases up to one value where it becomes constant. It becomes constant because the eccentricity become equal to 0. Okay, the eccentricity has been dumped to 0 at about 1.5 million years. So when this happens, the same major axis stops decreasing, and the system, the planet, the inner planets, no more falling. From this point on, only the tides on the star will act. So the source of the angular momentum will come from the rotation of the star in that case. But in a time scale that, and a small calculation has shown that from this point on, the time life of the planet is about 1 giga year, 1.1 giga year. One important point is the following. Okay, we do not know where we are in this process. We are somewhere in the continuation of this life. So this does not mean that this happened exactly in the past 1 million years. So somewhere in the past it could have happened. But since then, the tide in the planet ceased acting, and only the tide in the star is provoking the evolution of the system, and the inner planet is slowly falling down. Now the rotation of the planet. The rotation of the planet, okay, here is the period. So this is quickly reached, this point. There is some oscillations here that doesn't appear in the figure. The planet quickly reaches this situation in which okay, this is the orbit, and the planet reaches this situation here. Look that this value is far is larger than that one. So since we started this problem with a large eccentricity of 0.3, we have a big difference between the periods of the planet and the orbital one. But as the eccentricity is coming to 0, the two periods come together, and when the eccentricity becomes 0, the planets become exactly synchronous. But it only becomes synchronous after the eccentricity is equal to 0. And this is one point that over which we have many, we don't know exactly what happens. We have to use models for the dissipation as function of the frequency. As I told you before, in the formula used by Mignard or the Eggleton or Marley, etc., it is intrinsically assumed that the dissipation is proportional to the the inverse of the dissipation is proportional to the frequency. Then it's proportional to the velocity of the tidal wave. Then we have this result. But There are people that believe exactly in the opposite, and there are papers like the one paper by Gordon that shows that it can have a completely erratic variation. There are sort of resonances in which the dissipation becomes larger for that frequency than the neighboring frequencies. So this is one point for which the physics is not yet satisfactory. So this is what corresponds to the most common models used for tides.
Sylvio, where do the spikes come in your plot? There was one-
The spikes are resonance crossings.
It was the same in the eccentricity plot.
The same in the eccentricity. They will appear better in the yeah. So some complementary information just to fix ideas. Love number of 0.3 and Q Earth-like 2030. Maybe this the real value is larger because CoRoT 7b is too hot. At least the mantle is completely lava liquid, so it must have a value of Q which is different, which is larger than the one for the Earth, but who knows?
I mean, the Earth's Q is largely due to ocean tides.
Yeah. Yeah, in that case you have a very huge shell of lava, so it may be also high. Okay. Eccentricity evolution, and this is the blue line here corresponds to the conservation of the angular momentum because I have two planets, okay, and the two orbits are the parameters of the orbit are changing, but as far as the tide will only affect the parameters of the inner orbit. So the pair inner orbit, outer orbit will have angular momentum conserved. So this is the blue line, and this is the variation that we get from the simulations. This is the spikes that appeared in the other figure. Here they are more clear. They correspond to crossings by the resonance. In the crossings at the resonances, the eccentricity of planet B has a big variation, but it's immediately bring back to the equilibrium value given by the stationary theory. We can do the same for same major axis times eccentricity, the same kind of behavior. To see the physics, the angular momentum conservation, we use now a hypothetical model that enhances some aspects, some effects. The inner planet will keep it with 5 Earth masses like CoRoT 7b, but the outer one we put 1 Jupiter mass, so a big planet. Semi-axis given here. This is inspired by a model that has been previously studied by Joe and Lin. Evolution of the same major axis. Okay, the same major axis of the second body remains almost constant. The same major axis of the first body decreases. I will come back to this in a moment. Eccentricities. Okay, you have this behavior. What is interesting is to look here in the short term. What you have is no matter where you start with your initial eccentricity, it will adjust itself immediately to an stationary value corresponding to the dynamics, to the secular dynamics of the two planets, the inner and the outer one. And this value is this one. The eccentricity will adjust itself to this value. If I have only the inner planet, it will make this blue line here. It's very quickly dumped to zero. The eccentricity is very quickly dumped to zero. Since I have the other planet, and so I have an extra source of angular momentum, so what happens is that it will be frozen at the equilibrium value for the system. Okay, this is short time scale. Okay, in long term it is also decreasing and will go to 0, but not so fast as in the case where the planet is alone. So now going back to the other one I have shown here is the fall of the planet, is the same major axis. This is the other case. It quickly stops, it stops falling, okay? So the eccentricity comes to 0 and the planet stops falling because of its own, the tides provoked on it. While in this case, since the eccentricity is not dumped to 0, it is kept at a frozen value, the dissipation, the energy in the orbit continues and the planet continues falling, okay? The process is much more efficient than when I have just one planet. Okay, joint variation of E and d pi, delta, the difference of perihelion. What is interesting to see here is that the system goes to alignment of the orbits. This is the reason because in the other case, in the case of CoRoT, we start already somewhere here. We don't last time with what would exist before because it would not make much sense. Okay, this is a picture on the dynamics of the secular dynamics of two planets. The secular, these are the phase pictures of the variation of the orbits of two planets. In the secular variation, we can always consider the same major axis as being constant. The variations are of higher order, and we can relate the angle between the two orbits and the average eccentricities. This is the phase space of the average problem, so I am not looking at the terms with the same period as the orbital period of the motion. So in one system, like say Uranus, Neptune, okay, you have one given value, and the perturbations, mutual perturbations, make that the system can evolve in this way, always over one of these lines that works like constants of the motion. In this case, because you are losing angular momentum, the system is trying to dissipate, to lose its angular momentum, it spirals quickly to one of these points. In the case that I have shown, it spirals to this point. Okay, let me say that these two pictures are equivalent. The only difference is here is the eccentricity of the inner body. Here is the eccentricity of the outer body. So this point here is there. So the variation here is more like this. So the eccentricity spirals to reach this point. You see clearly this in the previous figure. Yeah, you see the eccentricity is oscillating with damped amplitude, and delta pi starts circulating and then oscillating up to reach 0. So when I reach this point, there is no way of continuing because I reached the center. This is an unstable point in the equations of the motion, of the average motion, as far as the same major axes are kept constant. But the same major axes in my case are not constant. The same major axis of the inner body is slowly decreasing. So what happens is that this figure is for the conservative case. In the dissipative case, what happens is that the scale of this figure is crunching slowly. So this point is moving towards the center. The center is here, 0, 0, okay? The center is it. This point is moving towards here. But in what concerns the dynamics, it is frozen in this position. It is frozen in this position, but this position is no longer fixed, but it is slowly going toward the origin, toward zero. The question of the angular momentum, okay, so I have the angular momentum of the first orbit, the outer orbit, and the rotational angular momentum. This is a very small number. I can forget about it and look just at these two. What I have shown you is that quickly this quantity E1 reaches a position in which it remains frozen. Okay? Frozen meaning in this case almost constant, but with very, very small variation. The same major axis of the inner planet is decreasing. The planet's falling down on the star. So this quantity here is decreasing. The angular momentum cannot be changed because the chance of the angular momentum are coming always from the rotation of the star, this very small term here. These are two different scales of magnitude that are being considered. So what happens here is that this quantity must increase. This quantity must increase. This A2 is constant. So the only way is that A2 decreases. So this explains why I have in the simulations always this kind of behavior. Not only because there is no tide acting on this body. The tide is acting only this one. Okay? The tide is making this eccentricity decrease. And the conservation of an angular momentum is such that there is an interplay between the two, and the eccentricity of the outer body also decreases up to the point of when this one equals to 0, it stops decreasing, or at least will decrease only due to the same major axis, which is much smaller. Okay. This was what I had to tell you. Now, my co-authors, Michenko is my colleague, Rodriguez is one student. Thank you.
Sylvio, what is known about the central star? What is the spectral type? Is there a good age estimate actually? What would be
G95.
G95 and any age estimate? How young?
Between 1 and 2 gigayears.
Oh, okay, so then it's very answered.
Yeah, between 1 and 2 gigayears.
Is the amount of energy dissipated during this very rapid evolution interesting? Is that an interesting?
Sorry?
Is the amount of energy that would be dissipated during this, talk about 1 million years for?
In the body.
Yeah.
Well, in this period, initial period, in which the rotations are it's not synchronous. It is certainly dissipating a lot of energy, but it stops when the eccentricity becomes equal to 0, because then it becomes synchronous, and there is no more the mechanism to make the energy be created inside the body. There is energy dissipated inside the star, but this is minimum quantity. And in the discussion, I told about the Q of the star. In this case, Q is taken 10 to 6, 10 to 5. We don't know exactly which value to take also. The people that has studied this usually take 10 to 5, 10 to 6.
But if it were 10 to the 5, then that would do something over the
What?
age. That would do something over the age of the system, wouldn't it?
Yeah, yeah. Sorry? No, with not the age, but the time it will still be existing.
Yeah.
Because the age is from the moment that the star is being created. So between the orbit at that moment, the orbit now, okay, it will affect the time scale. but not the time scale for this important part that is the part on the tides on the planet. Only,
Right.
only later.
But it becomes, if the Q of the star is too small, it becomes a problem for the survival of.
If it, yeah, usually it is assumed to be around 10 to power 6. All authors that I have seen always put 10 to times power 6.
Doesn't mean
This is
that's
a point
right.
that can be discussed.
If it is 10 to the 5, how long does it take for the planet to spiral into the star?
May you repeat?
How long will it take for the planet to spiral into the star?
About 1 giga-year in this case, from the current position. If Q is equal to 10 to power 6,
And how
obviously if Q is at 10 to power 5, it will be 10 times faster.
So the age of the system is 2 giga-years, and it takes 1 giga-year to spiral in. Is that what I'm understanding?
Sorry, Richard.
The age of the system is about 1 to 2 giga-years,
Yeah,
and the time for the planet to spiral into the star is also about 1 giga-year
from now.
from now.
From now. So we compute it from now. We take initial condition, the orbit today. Okay? So it has 1 giga-year more before reaching Roche limit and being destroyed. Okay?
So perhaps you could explain how you imagine the system was set up to start with, because this very rapid evolution would be, say, shorter than pre-main sequence lifetime. So, how?
No, I know. I have not studied the
I guess what I'm
The star
wondering
itself.
is, if it happened so quickly, then if that was right at the very early time, the star might still be contracting
Yeah.
to the main sequence. And
No, this I cannot tell you.
Do you expect the outer planet's inclination will also be damped?
Sorry?
The outer planet's inclination would also be damped?
Yeah, inclination.
Yeah.
Well, I forgot telling that, okay, for the inner planet, since we have, from the geometry of the transit, we can estimate that the inclination over is 80 degrees with respect to the tangent to the celestial sphere. Okay? And so we assume that both planets share the same plane with 1, 2, 3 degrees of difference, no more than that. So in all these examples, all these calculations, toy model were coplanar, not considering inclinations.
But if it's not coplanar, would it damp? If it's initially not coplanar, would it damp its inclination?
I think so. I think that at least for a few degrees, this it would the changes would not be important. Usually, these equations, well, the equations that have been used, the model could easily, but it is valid also for the three-dimensional case. But we consider the initial conditions corresponding to coplanar orbit. If we change a little bit, I think that the change will be not important.
Typically,
Okay, if I put like that,
inclination damping by tides is about 4 or 5 times the time scale for orbital evolution.
It's not some factor of the eccentricity damping? Okay.
You're relying on the rotation of the star to provide a symmetry axis, aren't you, in order to damp the inclination, I think. So if the inner planet was aligned with the equatorial plane of the star, which is rotating, but the outer planet was not, then there would be an increase in the inclination of the inner planet, which would damp through tidal interaction with the star. I guess that's the only way you can get rid of the inclination of the system. But I imagine that takes a long time. That's a relatively slowly rotating star, isn't it? So
well, it's interesting to say that to tell that recently, in 2 cases, it has been found that the star is rotating, the planets are retrograde with respect to the motion of the star. In this case, we don't know. Nothing has been done to see, at least till now, to know how this star is rotating. But the kind of behavior of the activity, if this activity is due to spots, I would not discard the possibility of having some tilt in the system.
Is the measured inclination of B consistent with C being both coplanar and not transiting?
Sorry, the first one, the inclination can be known from the fact that he is passing in front of the star. So we know the size of the star, we know where it's passing, we know the geometry of the orbit, we can make estimations of the inclination. In this case, 80 degrees, as I told, or 10 degrees, if I consider this the other direction. But for the second planet, we have no information at all. So it is assumed that they are equal, only.
Okay, and assuming that they're equal, is that consistent with the fact that C does not transit?
Yes, because it's much more far than the other one. So with 80 degrees, since it's more far, it passes over or below the star. No transits. It's a pity. It would be fine to have two both of them transiting. Okay.
Does the obliquity of the planet make any difference? You assume that its spin is aligned with the orbit.
If there is a tilt in these planes, many things will change. Yes, if you have an important angle, 2, 3, 4, 5 degrees, no matter. But if you have 30 degrees, okay, you have.
Would you expect it to be? I mean, the obliquity of the terrestrial planets is not.
For instance, yeah. No, in this case, everything was supposed to be well behaved.
At the end of your talk, you just described a model that we say super Earth and the giant planet. So why do you need this model to excite the eccentricity of the?
Sorry.
During the
the last thing.
Yeah. So why do you need this model? Because this model you use a gas giant and the super Earth.
I take it from you.
I know, but why you need this model?
If I when we have larger masses, things happen more with larger intensity. Okay, so it's easier to see the phenomena appearing. Okay.
In current system, they are with comparable mass. That's quite different with what China.
Yes, but the phenomena due to the secular interaction of the orbits is the same. The same as that we observe in one case, we observe also in the other.
Well, my opinion is they are still different a lot. Because if it is one gas giant or one planet, and really two.
But this was just to one more example. Huh?
Okay, I see.
Okay, I'm here till October 15th, so if you have any other questions, you are welcome.
Brilliant.